Next talk is the srsRAN project overview and roadmap. And so the idea here is to give you an idea of the current status of the project, talk a little bit about the background of the project, where it comes from. From that, talk a little bit about our ambition, talk about the future and where we want to take it. And then we'll go into a more detailed technical update and roadmap for the next couple of months. So first off, the project status. So this is our first project workshop, and I think the timing is very good. Roger already highlighted this, but it's 10 years the first go to what was libLTE at the time, that became SRS-LTE and is now srsRAN, which hopefully we can keep for more than 2 years. We'll see. Since then, we've grown quite a bit with srsRAN 4G, our LTE software suite, and srsRAN project, our 5G Open RAN CU and DU solution. srsRAN 4G is now 10 years old. We've got over 3,000, we've got over 1,004, and there's about an average of 1,300 views per day on the repo. srsRAN project is about 10 months old, and we're lag behind in stars and in forks, but we have an average of about 2,300 views on the repo per day, which I think bodes well for the future. Within srsRAN 4G, over 10 years, we developed about 800. In just under 2 years with srsRAN project, we've developed over 900,000 lines of code. And I'm spoiling Ismael talk here, but the snapshot of the performance is that we're currently running 24-hour 30 UE tests with peak throughput on via VTM500, reaching about 1.4 gigabits per downlink. So we're seeing that stability, and that's on a Dell XR12 with an Intel Xeon Gold 5317. And this is a CU and DU wraparound testing with a split 7.2 interface directly to the TM500. So the performance and the stability, I think, is starting to get there, starting to get interesting. We have a very active discussion board that we only launched in the past year. We're seeing an average of about 2,000 unique visitors per month, very good engagement on the discussion board. And our documentation continues to improve, and we're seeing about 7,000 unique visitors per month across both our 4G and 5G documentation. And when we look at where those visitors are, we have a pretty good global spread. So this is a snapshot of visitors over 1 month just to the 5G project documentation. But the measure of success really needs to be what could be achieved with the code. And within SRS, we've done some pretty interesting things. So we've had a heavy focus on air-to-ground networks. We've demonstrated handover at Mach 1, doing flight testing for US DoD. And we've built air-to-ground networks based on 4G, where we demonstrated links over 400 nautical miles. And most recently, we've launched a commercial network with Smart Sky Networks here in the US. And with Smart Sky Networks, we've deployed across 350 ground stations, coast to coast. And this is an air-to-ground network, primarily for business jets. But across those ground stations, we're running 700 instances of srsRAN. And that's a production network that has been live since about October 2021. Going further, we've deployed srsRAN in space. So for quite a few years now, we've been working with AST Space Mobile. AST are building a unique direct-to-mobile 4G and 5G network from low Earth orbit using large phase array satellites. These create beamform cells roughly equivalent in size to terrestrial cells on the ground. So we've been working with AST since the concept phase. The original implementation of their 4G stack was SRS-LTE modified in order to be able to handle the latencies around a low Earth orbit bent pipe architecture. And still today, we're carrying out active R&D with AST Space Mobile. And the software is being used to test this network across the US today. But for an open source project, it's not just what you can do with the software yourself, it's what others can do with it. And on that front, there's been a hugely diverse range of tools and applications built on top of the software that's been put out there. So we've seen multiple search and rescue drone implementations, including at least one commercial operation. We've seen false cell detection tools. We've seen broadcast receivers for 5G. We've seen passive sniffers and analyzers for LT. We've seen wireless intrusion detection solutions. We've seen large store customer loyalty and footfall solutions. Roger already highlighted the the peer-reviewed academic and industry research papers that we highlight on srsRAN.com, our project website. And since 2015, we've been tracking these papers, and we've got about 300 listed so far. And these are all published papers from researchers who are actively using srsRAN software on a day-to-day basis and within the publication itself. And these are coming from across leading industry, government, and academic research institutions. You'll have already seen that security is a big focus for the workshop here. And the GSMA maintains a mobile security, it used to be called the Hall of Fame, it's now called the Research Acknowledgements. And since 2017, there have been about 41 coordinated vulnerability disclosures through the GSMA. And by my count, more than half of these disclosures have been made by researchers who discovered vulnerabilities using it. These include vulnerabilities in wireless emergency alert systems, including presidential alerts here in the US, detection of security misconfigurations in public networks. And I'm very much looking forward to Youngdae's talk later today and Syed's talk tomorrow, specifically on the security research that they've been doing. So a little bit of background. So this is going back about 10 years. Two guys with full heads of hair and a very but even then, open source was in the DNA of the company. So the open source came first. LibLT project came before software radio systems. And SRS really has just been a vehicle for embodying that and pushing it forward. There, a little bit less snazzy logo, but a dedicated team of 25 people. And we've contributed 1.75 million lines of open source code into the community. Over 10 years of creating and publishing open source software. And key to that growth has been our dual license model, our dual license approach. We write software, we release publicly under AGPL v3, and then we provide the same software under commercial licenses. And this provides a really powerful flywheel that has allowed us to grow over that 10 years. So it has allowed us to bootstrap the company through R&D funding. The fact that we're creating and publishing open source software is of value to the funding community and to the research community to provide a platform and tools for research. It has required us to keep the code base very clean and be very careful about the software bill of materials, which is a key point. So if you're going to dual license, you need to be incredibly careful about how you design your software in order to be able to satisfy both routes. A big part of that is making sure that the software itself is self-contained. It's portable and it's clean. And that is a win both for the open source side and for the commercial side. It gives you that flexibility and it provides a much more, an application with. On the commercial side, commercial engagements have really required a higher bar for quality and performance. And so they've been a forcing function for us to really drive the performance and the stability of the software. And then commercial revenues from licenses and related services, feedback allow us to grow forward the open source implementations. Okay, so that's where we've come from. Next, I want to look at where we want to go next. So what's the ambition? What's the future for srsRAN? So for the first 4 years of the project, we really focused on 4G implementation. So between 2014 and 2018, we built the U, Node B stack, and we built a lightweight EPC. From 2018 to about 2021, we spent 2 or 3 years focusing on improving performance stability, adding features, hardening the code bases. And that was really driven by our commercial engagements during that time. In the next, we implemented initial 5G solutions, but we were building on the same foundations as we did for 4G. And then in parallel at the same time, we saw that the mobile wireless world was changing and big things were happening. So the growth of Open RAN and decoupling software from hardware. Hardware platforms were becoming available for Open RAN, and the industry was starting to shift in that direction. At the same time, spectrum was becoming more available for private networks in particular, both in the US and in Europe, and further afield. And non-public networks were starting to grow in popularity. In parallel, there was a great recognition of mobile networks as critical national infrastructure. And so there became a need for more supply chain diversity and more of a government and defense focus on wireless implementations. And so right now, we see a huge amount of activity around open source for Open RAN. There's a lot going on in various different bodies and fora. But we see a desperate need for an open source CU and DU specifically for deployment. And that's the missing piece of the puzzle that all of the other activities require. And I firmly believe that we're at a moment in time now, which I would call the Linux kernel moment for RAN. Thiago referred to it as the open flow moment for RAN, where there's an opportunity to provide this fully open source CU and DU solution for deployment. Not just for research, it certainly would enable research, but to be deployed in the field. And this is exactly our ambition. So we want srsRAN to do for mobile wireless what the Linux kernel did for operating systems, what OpenFlow did for wired networks. And so this is really what for srsRAN project, for our CU and DU. We, 2 years ago, set our ambition to develop the Linux kernel for RAN. What would that look like and what would that require? And so that's what we've been working on for the last 2 years. And so we went back and we rebuilt the foundations, went to a blank page and said, okay, let's build this from the ground up and design it for scale. And so this is the CU and DU that we currently release through srsRAN project. And when I talk about designing for scale, it's designing for a massive real world deployment. So we want this to be the default for anyone that's building RAN use cases. We want to build for flexibility. So it has to be self-contained and standalone, but it has to be easily adapted. So we're building in split 8 plus split 7.2 on the front haul. We're implementing our own front library. We're providing a CU DU fast path for implementing or deploying the CU and DU together on the one machine. We're adding optional support for hardware accelerators. We're adding optional SoC support with a FAPI interface built in from the outset. And when it comes to hardware acceleration, there's a lot of discussion at the moment of inline versus look aside. When you're building a RAN software stack that needs to be deployable and maximally flexible, you have to support both equally. And that's what we've been trying to do. But beyond the code base itself, when we think about scale, it's as important the engagement that you're going to have with the community around a fully open and deployable CU and DU solution. How do you manage the contributions and the modifications and the engagement that's going to come from the community around that? And so built into the code base is a software architecture, which has specifically been put in place to envision this and architecture and interface separation to make that task much easier. And so we're very much designing with that in mind. And so we're making all of our elements plug and play while not sacrificing on performance. And so this is where we are today. And we do have a solution, it's complete, it's portable, so we're not tied to a single hardware platform. Intel, ARM, AMD work out of the box. It's performant, we're starting to prove that with tools like the TM500. It's flexible, so we're starting to show ways in which this can be modified. It's interoperable, so we're already integrating a wide variety of open RU devices, and that list is continuing to grow, as well as support for third-party core networks and third-party RIC and SMO frameworks. And finally, it's open. And so we've taken this abstract architecture and embodied it into the code. And this is a diagram that we've taken from our new developer's guide that was just pushed out in the last 2 days. And so with this developer's guide, we're trying to start, but explain very clearly how that maps to the code that we've implemented. And so when you look at this diagram, all of the diagram map directly to the code base. So it's a map for the code base. And we're really trying to help the community to get engaged with the code through tools and documentation like this. So it'll take more than code to build the Linux kernel of RAN. We're working on multiple fronts. We're developing the code, we're developing the documentation, we're really pushing community engagement. But it's going to take much more than just SRS. It's going to take a much broader community for this to really be successful and to take off in the way that we want to see. And that's a key objective of this workshop. And we're really pushing towards that long-term ambition. And so with that, I'm going to hand over to Ismael for the technical update and to take a look at our roadmap.
Maybe this is better here. No? Hello, can you hear me? And this is, okay. Yeah, so as Paul was saying, we started almost 2 years ago, but the first year was pretty much no coding, only PowerPoint slides, blank piece of paper. We put a lot of attention on designing a very clean interface. A lot of this merit goes to Borja. I don't know where is our guy here, but if you find him, he is our lead expert in software architecture. There he is. So if you can grab him these days, you can ask him questions about the software architecture. Because we put a lot of attention there to precisely to allow other people to contribute, to plug and play different blocks, and to make it easy by inspecting the code. What are the interfaces between the different blocks, how each block communicates to each other. So we started probably writing most of the code around summer last year, and the first release came in I think March or April, and the second one last Friday. We are still aiming for 2 releases per year, like we did in srsRAN and srsLTE. But now we are doing something that you have probably realized, that we are pushing very frequent releases. At the beginning, we were aiming like 2 every month. But now we are going to relax and maybe do 1 every month. We can do this because we have improved a lot in our CI/CD. That's another thing that we did a lot of work last year. We will talk about this tomorrow in the tutorial. But the better CI/CD and code coverage allows us to release more frequently without having to do a lot of manual tests. So let's see what happened in the last year. So this was the initial release of the code after being 1 year silent. The code could already do 100 TDD or 50 FDD, and it was achieving a performance of 700 minutes per second in the downlink and 100 in the uplink. This obviously depends on the TDD pattern. We were already supporting 15 and 30 kilohertz, and it was doing MIMO 2x2 in the downlink, 1 layer only in the uplink. 256 QAM in both uplink and downlink. RRC, everything that is required for the session establishment, so security, authentication, connection request, all this, but we still didn't provide mobility, paging, or establishment. The MAC procedures, most of them except power control and our headroom reports also were MAC. And we added support for SPLIC6 using FAPI. This is something that in this new architecture comes directly from the beginning. The connection to we didn't support RUs. We only supported ETUs using this. So that's just what we can say. In terms of performance, at that time we were already testing, already doing 24-hour operation. And the bit rate was the full rate on a MIMO 2x2 cell. From April to October, the most important one was the 4-layer downlink. Not only the MIMO capability, it's the most critical there is the performance. It doubles from 700 to 1.4 gig. And that's once your algorithms are already very efficient, you can only achieve that by parallelizing more, but parallelizing more has always more complexities. So this is what took us a lot of the time. Test of the uplink performance. That's according to 30 for one. We are doing this in PUSCH only, but the rest of the don't tell anyone, but we have a lot of mobility already, and we are actually doing mobility tests in our lab, but we like to be quiet about our announcements because we want to test them very well. But we're starting to do mobility internally. Another big task this year was E2. If you want to talk about E2, find Justin Talon. I don't know where he is. He's probably there. He has a presentation later, and he's our expert on E2. He has added support for the KPM and RAN control service models. Are used using a split send.2. I'll talk about this later. And support for accelerators using BBDEF. So BBDEF, I think it's standardized in workgroup 6, I think, of the ORAN specs. We have integrated with the ACC100 FEC. We have it in the lab, and we are running tests every day. In theory, according to Intel, the support of the new vRAN boost accelerators, I don't know if you have heard about that, in the new Xeon 4th generation, they have integrated the FEC accelerators inside the chip. So now you only need to buy one Xeon and you have FEC accelerator. And we have also done a lot of effort in also optimizing and supporting ARM architectures. I will talk about this also in a second. So yeah, and then performance, the same stability. We are not able to test more than 64 UEs due to resource constrictions of testing equipment. So this is as much as we can test. And the performance doubled, essentially, thanks to using MIMO. The open fronthaul has been a very important development also. The first thing that we tried when we started looking at this was, okay, let's see what's out there available and see if we can reuse it to avoid reinventing the wheel. What was available was XRAN. XRAN, don't confuse with FlexRAN. Both Intel, FlexRAN is the full PHY and builds on top of XRAN. XRAN implements only the 7.2 interface. So that's essentially building the easy prepackets with the ORAN fronthaul protocol to control an RU. This is user and control plane. We took a look at the code, and initially we really tried to see how we could integrate it in our architecture to avoid reinventing the wheel, but we weren't happy on the quality of the code and how we didn't feel that the code architecture matched ours, and it was really difficult to put it in a way that it would follow the same architecture that we were designing. And instead of having it as an external dependency, what we decided is to just build our own fronthaul support, and then that allows us to have full in-house implementation of all layers from L0 to L3, let's say. Another advantage of not using XRAN is that the dependency on DPDK is optional. That's also a good advantage because DPDK, although it's open source, the license is not entirely OSI, and so that means that there can be some restrictions depending on the processor that you use it. And also it's a little bit complex to install. In many cases, if you are doing R&D research in the lab. Maybe if you don't need more than 50 megahertz bandwidth, you really don't need to bother. Or native OFH implementation without DPDK will be enough. So that's one step of the installation that you avoid that, to be honest, is a little bit painful. So that allows us to port the support to ARM, AMD, or any processor that we want. We have tested up until now with the Foxconn, the Venatel, and the Picocom are used. We are now starting to test with Xilinx and analog reference designs. And also very importantly, we have tested with the TM500 from Viavi. It has an RU emulator. And there are also, we know there are partners who are testing with the Keysight RU SIM emulator. So there is an awful lot of testing already on this front-hole interface. I think that this is probably what I'm personally most proud of the last months when I saw the team that were able to achieve this performance were really satisfying. And quoting one guy in LinkedIn when we posted this, there was one guy who said, Viavi doesn't lie. And it's true that when you're able to test your software at high performance with Viavi, that's a different story than when you're using other test equipment or even your phones. Because Viavi is really tough to integrate with. You need to comply with the spec. And you can't make any shortcuts. So when Viavi is telling you that this is the performance that you achieved, it's because it's true. In these cases, with only one UE, and we were achieving the full rate of the capacity of the cell. This one is with 32 UEs. And this test, we left it running 24 hours. And this is something that we are starting to integrate in our CI, that every night it will run automatically with the latest push of the code that night. It will run all these tests automatically. This is something that we are starting to integrate. Now, this is also another thing that we have added recently is the performance analysis of our receivers. We started with the PRAC, and the PRAC, most of the configurations, I would say that probably 90% of them would already satisfy. And then we moved to the PSCH, which is probably the most critical one. And here you see a plot of a comparison between the MATLAB and performance and our performance. This is a typical test. How is it defined? They say that for this given SNR, your throughput has to be higher. And for both 2 or 4 receiver antennas, we satisfy the throughput. This is only one particular channel model. In fairness, it's the easiest. But we are starting to do the same analysis with the rest. This analysis with the MATLAB set of tools that we also open source. I will talk about this tomorrow. For those doing R&D in L1, that's very useful. It essentially allows you to build. So it already provides end-to-end simulations or scripts to allow you to simulate a channel with some impairments. But you can very easily replace the receiver with our receiver from written in C++ that you can generate a MEX. So that means that you can easily make some optimizations on some changes and very quickly test that it still satisfies the requirements. Again, related to the CI/CD, every night from very long test vectors that we have generated using MATLAB, every night we verify that our C++ L1 layer still complies with the specs. On ARM optimization, also we did a lot of work. We optimized some of the code on the DSP, but also on the front-hole interface. This is an example of a test with doing 600 megabits. So this is 100 2x2 cell using an Ampere Ultra, which I think that has like 80 cores, 80 very small ARM cores. And these kind of platforms, when you say 80 cores and you think, oh, that's an impressive amount of processing, but it's very, very to distribute this processing efficiently. And at the same time, also, Andre here, I think that he put together this fairly quickly, this demo on a very small embedded Raspberry Pi. The challenge here was that this guy has very low memory, very low processing, so it's not so much about parallelizing, but more about fitting the code here. And this was a 5 MHz FDD cell. He could achieve connectivity with a code GUI and do reasonable rates. So how the future looks like. As you see, we are not super ambitious in terms of you won't see FR2 here, you won't see ultra low latency, you won't see mini slots. Because as Paul has been saying before, deployment and stability is our first goal. So we don't want to be the first ones to provide all the features. What we want is to make sure that when a feature is available, is robust. This is why I was saying before, mobility, we started a long time ago, we started doing initial mobility, initial handover in our labs, probably 2 months ago, till the end of the year at least, because we wanted to test it very, very well. The end of the year, we are also aiming to complete the conformance testing of the uplink receivers and continue adding extensions to the E2 service models. Well, Justin will talk later more about the service models, but really the challenge here is to provide support for the RAN control service models. And the next big thing that will happen in the next tag release in 24.4 is the separation of the CU and DU. So you see that we always talk about RAN architecture from the beginning, but you see that now the G0B runs collocated. So how is this ordered? But the thing, we have CU and DU entities in our code, and they communicate with each other using F1 protocol. Control and UTP also uses E1 protocol. The only thing that we have not done is the packing. I guess that the most critical here would. Again, we want to be very sure of what we do, and this is why we're going very slow with this. But the current aim in this next release to support the separation of the entities and multiple RUs per DU and multiple DUs per CU, which is both are things that we are already experimenting with them. So we have already done a lot of work, but we want to test them. The last two are still not 100% guaranteed that they will happen. But we find that it would be very good to do integration with an SMO through O1. This is also not critical, but an important thing in commercial deployments. And we also started NTN release 17 support. And we expect to release at least some initial support by 24.4 also. And I think that, yeah, that's already time. So I will end here if you guys, so I'm ready to take questions.
Okay, and so one thing I forgot to mention actually, and I was very glad to see was Roger acknowledging Ben Wojtowicz in his work in OpenLTE. And certainly srs-LTE and srs-RAN wouldn't exist if it wasn't for OpenLTE and the direction that gave us. So happy to take any questions.
George, you mentioned the SRCUE briefly earlier. Just wonder, is any plan on that front in the foreseeable future?
I knew that was going to be the first question. Yeah, it's a very good question. So this is one of the challenges we have. So if we're going to aim for this ambition of a hugely deployable open source RAN stack, we don't have the resources within SRS to do both the RAN and the UE. And so we made a decision about a year, 2 years ago, to put our focus of our efforts on the RAN stack at the expense of the UE. Now, what I would love to see and what I'm hoping is that as we build this community more and as we expand the code base and the community around it, that the UE will be grown as well. I don't think SRS are going to be able to take responsibility for growing that. What I would say is that within the new RAN stack, all of the building blocks are there. There's a reference implementation in the 4G code base. And so everything is there in order to make it easy for the community to adopt that and to drive it further. Now, that may need encouragement, that may need funding, that may need support from external sources. But I think given the importance of an open source UE implementation to all of the security research that's been done, that's a very easy case to make. And so I'm hopeful that that will happen.
Hi, I was wondering, like you mentioned that your CI and CD pipelines needed to be greatly improved to allow you to move fast. I was wondering, like, if you could share a bit more, whether you have pictures, like what that looked like, because I imagine at the end of the day, you need to test with commercial UEs for a lot of this, right? And I having done so myself, like, it's a lot of difficulty in getting like instrumentation on those commercial UEs to figure out why sometimes they aren't working. And I'm wondering if you could share any of your insights and if there's any challenges that you solved.
Yeah, tomorrow in the tutorial, there will be a couple of slides, not a lot because there is a lot of content to talk about, but and also it's something that we can discuss later offline. But yes, it's testing with phones is very difficult. This is why every time we're doing it less, and we are relying on other tools like Viavi, which is a professional grade tool, or unit tests or integration tests, of essentially of smaller blocks. So if you are trying to test a big feature by connecting the phone with the G0B, it's very likely that every 100 nights that you run it, a few will fail, because even if you, for instance, trivial things like you have a shield box, but no matter how good this shield box is, but it will still receive some interference from outside, because you have, if the cables that you are connecting with a ref are not properly isolated, it will receive interference. And the phones sometimes suddenly decide to not attach to a network that we're every day attaching, or yeah, they attach, and if you are using an SDR, suddenly it can stop working also. So for us now, the key to the testing are the unit tests. So that's where we try to cover most of the issues, because it's the most reproducible. With the code UE, we just do a simple attach and iPerf to verify that they still work. And then the performance is done with Viavi in RU emulation, which also you can eliminate the RF uncertainties.
Yeah, that's certainly a topic that could take a full day's conference by itself. What I will say is that it's a topic that we've invested a huge amount in over the last 2 years. I would say next to the code-based development itself, testing is what we've invested in most. And so during the tutorial, there'll be certainly opportunities to go into that in more detail. And Neil's the member of our team who's focusing more on containerized deployment and Kubernetes, can certainly speak to how we've leveraged that for our CI/CD system.
Hey, thank you for nice talk. I have one recommendation. I see that the srsRAN is having so many parameters to configure, and then when we work with Open 5Gs, it is also having parallel development. But it is kind of very fragile to work on two different versions. Sometimes we spend a lot of time in finding out what parameter I missed to configure. If srsRAN can provide some kind of containers with the combination of the components of the srsRAN UE, UNode B, or GNode Bs with Open 5Gs, that would be very helpful.
So I'm sorry, I fully got it. So it's like Open 5G.
Containerization. So that's something we can certainly help with. So we're already doing exactly that for our CI/CD. And so I think if you speak to the team at the back of the room, we can certainly provide more information on that. And I think that there are certainly internal tools that we have that over time we hope to be able to release publicly, because I think it's going to be more broadly useful to people. Any other questions? I know we're between you and lunch. Maybe one more.
Hi, I want to ask you about the AST thing that you showed on the website. That is the beamforming feature is there. Right now, your DU don't have the beamforming feature. I mean, do you have a plan to do it in the future, or you are relying on RU side to take care of the beamforming?
There is no plan until the next release to provide beamforming. I guess that at the current private 5G market that we are addressing, that only uses 4x4 RUs, doesn't make a lot of sense. Certainly when we go to FR2 or higher order of antennas, then beamforming, I guess that in the RU will be the next big topic. The way we have designed the open front-haul interface is that, and all our code is that natively it's already supporting Cat A and Cat B modes. So we are able, the code is ready to support that. But again, the biggest challenge with these kind of things is availability of the hardware and then the testing. I think that there was a question there also, no? Yeah.
So the point was made earlier today that operators are reluctant to deploy Open RAN technologies until or unless feature, performability, security parity are established. And just to be fair to operators, I'm with AT&T, it's our customers who are insisting upon this. Have you thought about some strategies to introduce or insert srsRAN into an operator's embedded 5G LTE base and every step of the way demonstrating feature, performability, security parity?
Yeah, thanks for the question. And that's something we've been doing recently, actually, is, and then I'll speak to the GXE private 5G deployment outside. So one of the objectives in working with GXE was to be able to take their standard private 5G solution and swap in srsRAN instead of the software stack on that implementation. And that then allows us to do very straightforward side-by-side comparisons across performance, stability, security. And so, yeah, that is something we're very much focusing on. I think the challenge for us is there's a big jump from us to someone like AT&T. And so it's the smaller, non-public, private network deployments are where we see the opportunity to really prove our case and then move from there. Okay. So I think we'll finish up there for lunch. Throughout lunch and indeed throughout all of the breaks in the sessions, the demos are still ongoing. The SRS demo is in the Boston room. We have academic demos in the hospitality zone, and indeed we have the GXE deployment just over here. So we'll see you back here at 1 o'clock.